So I'm going to give an introduction to lattice reduction. And so this will be a little bit different from some of the other talks, a bit more theoretical, but perhaps hopefully interesting nonetheless. So you may ask, what is a lattice? And so the purple dots represent one two-dimensional lattice. We'll talk about lattice bases. And so the red arrows illustrate one basis for this lattice, and the green arrow is another basis. We'll come back to figures like this in a second. Another question you may have is, why should I care about lattices? Well, that's fine if you don't need to care, but perhaps a couple interesting points that even if you ignore the rest of the talk is that cryptography is a hot field now, and it's going to remain hot for a long time. One of the hottest areas in cryptography is the use of lattice tools to build cryptography that is secure against attack, even from really powerful future quantum computers. And it's also lattice tools are also useful for other cryptographic constructions like fully homomorphic encryption. So I'm going to give an introduction to lattices. Just as a brief note, my slides are available on GitHub. I shared a link in the chat to them if you're interested. So these lattices are useful not only in cryptography. There's lots of other uses. This slide has links to other uses besides cryptography. You can follow these links if you go to my slides that I shared with you. Okay, so I'm going to start off with some background. So, the right side of this slide gives some mathematical definitions of lattices. And for those of you that have a bit of background in linear algebra, I'll say that one practical definition is that is using a matrix. So given a basis matrix, B, and then for some vector of integers z, then we're going to call the resulting product, b times z, a lattice point. And we're going to say the collection of all such lattice points is a lattice, all possible b's times z's, all possible combinations of our basis matrix b times some vector of integers. So these purple dots, again, represent a lattice. And so one question you may have is, how many bases are possible? Well, there's an infinite number of bases. Here are two bases for this lattice. The red arrows represent the columns of the B-red matrix there, B-red basis matrix, and the green arrows represent the columns of the green B-green basis. So in many cases, we want to go from a basis that has long, not so orthogonal basis vectors like the red one to a basis with shorter and closer to orthogonal basis like the green basis. So I'm not going to talk about unimodular matrices except for possibly in the Q&A. But I will say that the way that we get a good basis is called lattice reduction. And if any of you have any linear algebra background, then I'll say that lattice reduction is kind of like a QR decomposition for integer problems. So let's say in the end, you want to come out with an integer, not a float or a real number, but an integer. Then perhaps instead of some QR decomposition or some other linear algebra decomposition, you want to use lattice reduction may be useful for you. Okay, so how does one do lattice reduction, you may say? Well, the most important technique is from Lenser, and Lavache. It's known as the LLL algorithm. Here's some pseudocode. It calls a subroutine known as size reduction. So I apologize for going so fast. If you have some background in linear algebra, you can come back and look at these slides later and figure out how to do it. But I'm not going to spend a lot of time on these slides, or even on this slide, which shows Julia code for an LLL. Rather, I'm just going to tell you what you might remember, and that is that the LLL is pretty fast, and it does a pretty good job of reducing the basis. In fact, its polynomial speed and acceptable reduction quality are what brought interest to lattice tools. Brought a lot of, okay, so since this isn't the focus of this conference is on open source software, then I'm going to share an open source tool with you called Ll.plus.jl. This is a Julia package. It has some lattice reduction and related lattice tools. It's also got some demo functions. And one of those, subset sum, is what we'll give a brief demo of. Before that, I'll just share with you briefly that if you pass in that that red basis, you know, our small two-dimensional basis into this lattice tool, then you do get out something effectively the same as the green basis, except for with a sign change on one of the coordinates. So it does work. And you can come back and copy this code into your Julia terminal if you'd like. But we'll go on to a small demo. And specifically what we're going to demo is solving a subset sum problem. So let's say we have a vector of integers, just a bunch of integers, and a sum s. And the question is there some subset of those numbers which add up to the sum s, our target sum? We got some integers, we got a sum. Do all or some subset of the integers add up to s? So there's an LL-based technique from Lagarius and Adlisco, which can solve this. And there was a time when this was thought to be a hard problem, so hard that the cryptosystem was built on it. But then, this technique from Lagarius and Adlisco breaks it. So this subset sum, this technique from Lagarius and Adlisco is useful for integer relations as well. Okay, so this slide describes what we're going to do, but rather than just looking at directly at the what's on the slide, we'll see if we can just do a demo. And Jesus, can you confirm that you can see this my screen here?
Yes, we can see it. Yep.
Great. Okay, so Julia has a REPL here, and I've just started it up. And one of our previous slides shows how to install the Ll.plus package. So I'm just going to use it. And because we're going to use numbers with lots and lots of bits, I'm going to set our precision to be kind of high. I'm going to use a set of 50 integers, each with up to 190 bits. It can be larger, I don't know, 256 or 1,000 bits if we wanted to. And we're going to generate this. So here we're generating our vector of 50 integers, really deep. I'll show them here in a second. And now we're going to pick off a subset of those and find the sum s. We're just going to go straight and see if we pass in that vector A of integers and the sum s into our function, can we find it? And so this elapsed macro here is going to tell us how long it took. So it took us 7 seconds there. Julia compiles the first time that you run it. And so the second time is just giving the execution time. So it took us 1.6 seconds to find this vector of integers. So let's just see. So let's kind of review what happened here. So we found 50 integers. They're really, really big integers. Lots and lots of bits to them. We're showing the first few and last few of these 50 integers. And we took some of those integers and we added them up. And we just passed the sum and the integers to our tool to see if we could find them. It did. In fact, our x and our x true are the same. So if we take the difference between s and this binary, this Boolean vector x times Hermitian x transpose times a, then we get 0. So we can go back and do a slightly simpler example if you'd like, but perhaps first I'll stop here, and this concludes the majority of my talk.